So far is we've talked about everything in trig. We've done right triangles, we've done our special right triangles. Our special right triangles helped us to derive how the unit circle worked. We worked the unit circle via all the different reference angles and all that kind of fun stuff. We therefore then set up and solved equations via the unit circle, whether or not it was within one revolution or it was in infinite revolutions on that, where you had to tack on pi's and stuff. And then lastly, we graphed. Well, the part that was left off, we kind of talked about with equations when we said this: cosine squared plus sine squared equaled what?
1.
It equaled 1. This was one of what we called a Pythagorean identity via trig functions. And we utilized this in our trig equations because sometimes you had a cosine squared plus a sine and something else, and you were able to substitute in to rewrite everything in terms of sines. That wasn't too difficult. But what we want to do is I want to show you guys that there are other identities and there are other things that we do. We can simplify trigonometric identity or trig problems via a whole ton of substitution. I wrote this as proof, and I know that in traditional senses of proofs, you guys did 2-column stuff. No, it's not anything like that. It's not statements and reasons and anything like that. It's just a ton of substitution. So let's go through some of the identities. Like these, which you already kind of knew. You know that cosecant is 1 over sine, which means that sine is 1 over cosecant. You knew that. You knew that secant was 1 over cosine, which meant cosine is 1 over secant. You might want to write this down. Are you guys okay if remember how I mentioned, oh jeez, a long time ago that I run into the tendency of forgetting to put x or theta or anything like that in there? Are you okay if I don't do that? The reason that I don't is because these identities won't work unless you have the same value for theta or the same value of x or anything. So we're just going to go ahead and imply that they're always there. I just get lazy and don't write it because it just gets really, really messy as you get going. So it's just another way of doing it. Okay. So sine is 1 over cosecant. They're inverse, they're reciprocals of one another. Remember that? Secant's 1 over cosine, so cosine is 1 over secant. Cotangent is 1 over tangent, which means, bless you, tangent is 1 over. And we also knew the other tangent-cotangent identities. We knew that tangent was sine over cosine because it's y over x, and so on. So let's see here. We have sine is 1 over cosecant. Cosecant is 1 over sine. Cosine is 1 over secant. Secant is 1 over cosine. Tangent, 1 over cotangent. Cotangent, 1 over tangent. Tangent, sine over cosine, which we knew. Cotangent is cosine over sine. And then the fun ones. The Pythagorean identities. The Pythagorean identities, we utilized that one before. We used that one to solve equations. We used that one when we had something that looked like sine squared x minus cosine x plus 2 is 0. Remember when we did that about 2 weeks ago or so, right before spring break? I said, hey, let's rewrite sine squared as 1 minus cosine squared. That's where that came from. That's why we use those things. Well, what happens here with these Pythagorean identities, there's actually 3 of them. And within the 3 of them, you can manipulate the equations by solving what we call a literal equation, which is something else that you guys have all done before. When you have a literal equation, like distance equals rate times time, d equals rt. Get t by itself, d over r is t. That's a literal equation. You're just moving variables around. Same thing with this. So you had sine squared plus cosine squared was 1, which meant if I isolate sine squared, I can say that it is 1 minus cosine squared. If I want to get cosine squared by itself, I can write it as that. Those are easy manipulations within those. You're just isolating a variable, if you want to think of it that way. Okay? The next two are 1 plus tangent squared is secant squared, and 1 plus cotangent squared is cosecant squared. I guess the only way that I was ever able to keep those two straight is that cotangent and cosecant start with the letter C. Okay, wait. Oh, remind me to show you a video. I have a very good video for you. It has to deal with that because it made me really laugh, and I thought of it right away. You'll be impressed. No expectations, or keep them low, but yes. So you have, if I wanted to get tangent squared by itself, what would I do with the 1? Subtract it. So I can say that tangent squared could also be secant squared minus 1. And then same deal here with cotangent. You can say cotangent squared is cosecant squared minus 1. And at this point in time, you guys are going, oh, well, why do we need to know all that stuff, Murphy? Where are you getting at? It just sounds like a whole lot of letters. Well, there's a whole lot of letters, that's right. We can do a lot of fun stuff. Let me write down the Pythagoreans on the side here so we keep those straight, so we don't have to keep going back and forth. Sine squared. I don't know how well I can see that. Sine of b divided by the tangent of b is, it's kind of not really politically correct anymore, but back in the day it was funny. Who is that? Cos b. Get it? Cos b, cosine b. Okay, well, the humor to me was funny. You guys can all, whatever. Basically what this means is this. I get it. If I take the sine over tangent, and I want to simplify that, I can break these things apart, and I can simplify my trig identities by breaking them down into smaller bits. Okay? Sine divided by tangent, that's a fraction. Everybody agree with that? That means I can rewrite it as sine divided by tangent. Or, I'm sorry, let me do this. Yeah, I'll do it that way, sorry. Everybody okay with that? Tangent can be rewritten in terms of sines and cosines. What's tangent written as sines and cosines?
Sine over cosine.
Sine over cosine. So then I can go and say that it's sine divided by sine over cosine. But when you're dividing fractions, what do? Yep, you multiply by the reciprocal. So you get sine times cosine over sine. And what happens? And what are you left with? And that's what we're doing, guys. We're going to take a trig setup, whatever you want to call it, with the identities, with just the sines, cosines, tangents, whatnots, and we're going to try and simplify it. We're going to try and simplify it by doing a whole bunch of substitutions. Yes, this is going to be a little bit of a pain in the butt at first, because at first it's so daunting about the idea, I don't know where to start. But if you follow a couple of the tricks that I'll show you here, by trying to rewrite things in terms of sines and cosines, and just kind of continually try to simplify out via by multiplying and crossing out things that they have like pairs of ones, you'll be okay. All right. It's kind of like working with polynomials, but not working with polynomials. So I know how much you love that. All right. Let's simplify these. Cotangent times secant. When you're writing these things out, guys, you don't have to put the value of x, because if this was x and this was y, you would just say, no, Murphy, I can't do that because they're different thetas, different angles. These are always going to be the same angles. I'm never going to give you one to trick you and say, you can't do it. So don't worry about that. I also don't put the x in there because it gets real messy. Too many letters. Words. So here's your first top tip. Cotangent and secant are both reciprocal functions. Do you guys, you know what I mean by that? Cotangent is the reciprocal of what? And secant's the reciprocal of what? Cosine. So what I want to try and do here is one of two things. I want to write them in terms of the standard functions, your sine, cosines, and tangents, or I want to rewrite them in terms of sines and cosines. So you can do one of two ways. I can change cotangent to becoming 1 over tangent, or cotangent in terms of sines and cosines is what over what? Cotangent's what over what? Cosine over sine. So this is cosine over sine. And secant is the reciprocal of what? Cosine. So how do you write secant in terms of cosine? It's 1 over cosine. Oh, what do you get? You get 1 over sine. I'm very pleased the fact that you said 1 over sine and didn't give sine a life jacket to float upward. Which equals what? Cosecant. Very good. And I can rewrite that then as a cosecant because then I get rid of the fraction. It's less writing. Okay. That's all it is. It's a whole ton of substitution. You know what? Honestly, you know all of these already. You know sine squared plus cosine squared is 1. The only two you don't know is the tangent squared and the cotangent squared. If you think about it, if you just start really going through like, oh yeah, they're reciprocals of one another. If you know that part, you're fine. Okay. All right. Now the next one, we have sine times the quantity 1 plus cotangent squared. Well, in this case, it's telling me that I need to distribute, or do I need to even do that? I'm shaking my head no, not because I have the twitch, just saying no. Because what's 1 plus cotangent squared? According to the thing written on the board on the right. Cosecant squared. This here is a Pythagorean identity. That equals cosecant squared.
Isn't it a -1?
Cosecant squared is the reciprocal of what? 1 over sine. So if it's cosecant squared, what would it be 1 over sine squared? It works the same. Okay? It works the same. So then you get sine times 1 over sine squared. And what happens? How many sines do I cancel? One of them. I can cancel out one of them because think of this as the same as x times 1 over x squared. You simplify it out the exact same way. The only thing that's changed here, instead of writing just the letter x, I'm writing the letters S-I-N. So this sign drops with the power, and you're left with 1 over sine, which is, you already know this one, cosecant. And no, not every answer is going to wind up as cosecant, which most people go, you always get cosecant.
So
They use that face too.
You also say that cotangent times secant is equal to sine times 1 plus cotangent squared.
Yes. There's a lot you can do. Some ways are longer to get to it than others. I've seen people go through and do like 8 or 9 substitutions, and they say, what did I do wrong? It seems like forever. I'm like, well, you could have done this right at the beginning and been done. It's one of those things. I'm not gonna lie, this does get kind of frustrating sometimes for students because there's so many different ways to get there, and you can just kind of get lost if you're not careful. I'm not gonna do any of those. Here's a little thing that is different. This is different than simplify. This is called verify. Verify is nice. The reason that I like verify is because it tells you what it has to simplify to be. It says, hey, knucklehead, cosine times secant, show how it equals 1. It's telling you what the answer will be when you're done. So you don't have that going, am I done? Should I get all the way through it? Is there anything else I have to get to? Nope. It's telling you, make it equal to 1. So this one's pretty simple. Cosine and secant, aren't they reciprocals of one another? So all you have to do to verify that this works is this. Cosine times 1 over cosine. And then what do? No. And it's verified. I'll buy it. All right, I'll buy it. Next one. Tangent, cosecant, cosine. This is a great example of how you are given multiple representations of the regular trig identities and reciprocals. Whenever I see that with regular trig identities and reciprocal trig identities and tangents, I always want to try, especially with multiplication, I always want to try and rewrite everything that I can in terms of sines and cosines. If I rewrite all of these parts in terms of sines and cosines, I might have more of a clear picture as to what's going to simplify out, okay? And I just go bit by bit. Since it's multiplying, it's pretty quick. Tangents, 1 over what? Sine over cosine. Cosecants is 1 over sine. And then cosine is just plain old. Hey, would you look at that? I love it when a plan comes together. Who said that? Robbie. It's the 18, BA brackets. You know what BA stands for? Yeah, that too. You don't even know who that is? Mr. T? I pity the fool? The 18? Big guy, mohawk, side hawk, lots of chains. Trap, we're getting old. And then sometimes the wheels come off. Sometimes the wheels can come off a bit. And this is where understanding of where it starts and where it ends comes into play. So we have the identity cotangent squared over cosecant. You want to show that it's going to equal cosecant minus sine. So what I want you guys to notice here, see how you start the problem as a fraction? and yet it ends the problem in subtraction, that means you had to be able to take a singular fraction and split it into two pieces. So if you were able to split something into two pieces, that denominator had to go to both parts. Okay? You had a common, you're taking a common denominator and you're breaking it apart. Think of it like this. I know that 4/5 could have been 1/5 plus 3/5. Do you agree? That's kind of the idea of where I'm taking the starting point, and I see that I have two parts after it, whether it's addition or subtraction. That meant somehow, some way, I had to come up with a common denominator that was able to break it into two parts. And it also works going from this way to this way. If I see two pieces that become one, that meant there had to be a common denominator that was generated. And we have plenty of examples to go through this. Okay? So if I start right off the bat, I see this cotangent squared and I see cosecant. I think of once I see a cotangent squared, instead of writing it as cosine squared over sine squared and doing all that, I know that cotangent squared has a Pythagorean identity to it. Over here, we wrote down that 1 plus cotangent squared is cosecant squared. If I want to isolate cotangent squared, what do I have to do to the 1? Subtract it. Hey, look where my subtraction comes from. So cotangent squared can be written as cosecant squared minus 1, which means via substitution, I can rewrite this as cosecant squared minus 1 all over cosecant. Do I now have two parts in the numerator with the same denominator? Which means I can break it apart, because this cosecant in the denominator would technically be the common denominator for the two of them. See how that works? If I utilize the idea of this common denominator, I can break apart the fraction. And now I can simplify each of those fractions independently. What's cosecant squared over cosecant? Cosecant. What's 1 over cosecant? Sine. Yeah. That's a good trick right there. Common denominators, working backwards to a common denominator. Have I lost you yet? Yes, Trap.
I don't get where you got the cosecant squared over cosecant.
Oh,
Did you do
this part here?
Yeah.
Okay. Remember a second ago when I wrote 4/5 was the same as 1/5 plus 3/5? What I did here was I'm working backwards. Instead of, see how these two have a common denominator, which meant you can write it as 4 plus 3, or 1 plus 3 over 5. This, think of this as 4 minus 1 over 5. That's the same thing as saying 4/5 minus 1/5. Since this is the common between both of these, because there's no addition or subtraction down here, it had to be in both parts. That means I can break it apart into two separate fractions. That's how that one works. A singular denominator can go into double or multiple parts of a numerator. We actually did this before when we did simplifying exponents back in chapter in October. We did this before by breaking apart a trinomial with a common denominator to simplify each piece of the trinomial. In this case, it just so happens to have trig in it instead. Okay. We'll do more, don't worry. Another verify. So I have sine over 1 minus cosine, and I want to show that that equals 1 plus cosine over sine. Well, it does. It's obvious. It already says it is. So why do I have to do the problem? Well, because there's trigonometric proof, and there's a method to do this that you've already done. What would you do if you had this? How would you simplify that? What's that?
By crying.
Well, crying never really solved anything. But if you had to mathematically do something, what would you do? Not by root 3. What would you multiply it by? 1 plus root 3. Remember what that was called? It starts with a C and ends in a conjugate. It's a conjugate, very good. We multiplied. Come on, I'm trying to help you out a little here. We multiplied by conjugates. We did this before where you multiply top and bottom by the conjugate. Because when you multiplied this out then in the denominator, it created a difference of squares. The difference of squares eliminated the root, and that made you happy. It's kind of along the same lines when you deal with trig functions. When I have, in this case, a denominator that has two parts to it with addition or subtraction, one way to get rid of that excuse me, is to create the multiplicative conjugate of the trig identity. It sounds like a weird way of saying something for this. Instead of 1 minus cosine, I'll multiply it by 1 plus cosine. Because 1 plus cosine divided by 1 plus cosine is 1. It's 1. All I'm doing here is I'm multiplying by some factor of 1. It just so happens to look like crap because you've got the word cosine in it. That's all. So from here, think of this as a FOIL problem for the denominator. But also think of it as a difference of squares. You have a minus b and a plus b. When you did that as a difference of squares, what was the shortcut? Do you remember? A squared minus b squared. Because that middle term would go away if you FOIL it out. I'd have 1 times 1 is 1, plus cosine, minus cosine squared. So the denominator here becomes 1 minus cosine squared. The numerator is just sine times the quantity 1 plus cosine. Now in that denominator, notice what you just created. Very good, Racky. 1 minus cosine squared is equal to what? It's sine squared. You created a Pythagorean identity because we know that sine squared plus cosine squared is 1. So I can put that there. So you use the ideas of those Pythagorean identities going back and forth and manipulating it out to see where it gets you. So now my denominator becomes, well, we have sine 1 plus cosine over sine squared. And what happens? The sine cancels out, which gives you 1 plus cosine over sine. And this gets a big, giant, super happy face because it takes a long time to get to it. or you could rewrite that as cosecant plus cotangent, but that's not for right now. It really make them mad. You guys okay? Should I have left the lights on? Man, it's early, you guys. Okay. Glad to hear that everybody's having a good time. Let's simplify. Let's try to simplify. So you have secant plus 1, secant minus 1. So, hey, look at the difference between the numerator. You have secant plus 1, secant minus 1. What is that going to equal? It's going to be what? Yeah, that's a difference of squares, isn't it? Not junk squared plus junk squared. Junk squared minus junk squared. So, what's the numerator? If there was only some identity that had the word secant squared and a 1 in it. Oh yeah!
Is there a trig
So I wonder, what could I do to get to make it look like secant squared minus 1?
tangent?
And there you go. Voila! That's French for voila. Is that French?
I think it is.
You're the French one.
Voila. What are you talking about? You were just telling me this morning about your coffee.
Cafe. Cafe Negro.
I'm
Es
cafe.
muy delicioso. Delicioso.
Now let Spanish please go.
Tray.
Très bien. Es muy caliente.
Tray bone.
It's very in Spanish. Oh my.
What's tangent squared divided by tangent?
I wish I was German.
Tangent. We never go off on
Of
those.
course you wish they had German.
German or Russian, they almost
Thank you for laughing. It's
so sick.
I tell you, it's never a dull moment.
Aw, never go.
Tanika's taking Chinese. She speaks
She is
Chinese.
Chinese.
Oh, we did this
Taiwan.
one.
She's
Taiwanese.
Cambodian.
Let's just take math.
Ooh, we'll do this one.
She's from Cambodia.
Where's Cambodia?
Mom's rose.
This is tricky. I don't know what to do. Oh no, what do I do? You need to work on your sarcastic I don't know voice. I hope you don't cry, because this is just math.
You're hoping I got it.
What would you do if somebody just started crying? Like, cause
I'd ask them if they were okay, and then
But
I'd.
it was because of math. Like what you were
Oh,
doing.
I've seen.
I've seen people cry.
I've seen
It's no
people
big deal.
cry. People cry. It happens.
I can't just cry on command.
I can.
Is there anything that you might see somewhere written on a wall, if it wasn't so dark, that has secant squareds and tangent squareds in the same, I don't know, sentence?
That one?
You know, that one where
What's
it's,
the one? Do you have to memorize all that
No, like
stuff?
seriously.
you need to know them, yeah. But I was just telling, like I was telling Reki, honestly, let me flip this light back on here for a second. And if you go back and you look at them, you know this.
Yeah.
You know sines, cosines, cosecants, secants, tangents, cotangents, you know all that. You also know sine squared and cosine squared equals 1 because we did that already. Well, kind of. We did that. So literally, there's only 2 new ones. And then if you know those 2, it's just a matter of being able to manipulate them around. All right. So here, if I move the tangent,
Why can't they all look?
because it's not that much fun.
It's not that much.
There's a lot more.
It's only a little bit of fun.
It's only a little bit of fun. All right. You're going to hate me when you see this. But I'll get over it.
I never want to hear those words.
You like how I just kind of come out saying, yeah, I know you're not going to like this, but
There you go.
It's gonna have like a huge packet of some sort.
It'd be like 2,000 problems, get this done.
Too much homework.
I can't do it. I'm already doing it.
yeah.
That's what you decided to do?
When I put my
You heard that too.
I think I just needed to see that.
Thing is though, I don't know if you know, understand how annoying it is. Questions. No offense. That's like infuriating. I'm serious.
Do you know how annoying it would be to copy the euro then?
That you did. So it's,
Oh yeah, that's true. Like, this is actually kind of a choice.
That's what I get for very early. You know, all these copies choices so far. Because, you know, photocopiers never work. So anytime you see it, they work. Like, oh, sweet, let's get this done.
I have to look at the Manny's question. If they're like symbols.
all of them are weird. Every
Oh, well. I'll just give you the big, giant packet of fun for now then.
Tell us only the good thing from.
No.
I told you there would be a packet.
Did you hear like the thump as he put it down?
I don't know. Can you
It's the
put it
packet.
together?
Yeah, you guys will love this.
Yeah.
How much of that do you want to do?
I'll tell you, no worries, no worries. We'll be working on this packet. That's not like the package.
I'm
of
peacing
that.
out for the rest of the week, so
He was like, I'm out.
And then when you're making
I'm
up
gone,
all
boys.
the words, no one's gonna help you.
I'm gone, my guy.
Yeah, then she's gonna get math chosen and be like, guys.
Yeah, and then you're like, I'm not gonna should have came to school.
Aren't these awesome?
It's gonna help.
They're, yeah, they're wonderful.
Where did you go?
No. The one that I can't find, which I've already made the copies of, is
I heard once somebody called you Max.
I know.
But I know, that's why I don't do that. I just did it because I know Sawyer.
He'll like text me. He'll be like,
Is
Madison.
this
I'll
one.
be like, man, you put
and
so
this one has.
Dude, okay, that was the funniest thing in the world. You looked at like your details and you were scrolling of like all the pictures.
Hey.
you sent.
Let's do this.
Like of your text messages of
On-
Sawyer, like details. And scrolled and it never ended.
Let's do the first page.
That would end.
Yeah.
And it's
Hey,
only
you
half
acted like I did not.
Because
You acted like I didn't say
Obviously,
anything.
as you start to piece through this, you will see that there
I
are
did, Emma.
upward complexity of these as we go
But I
along.
do.
It does tend to get a little bit
You only put it on your snap.
interesting to say, shall we say.
She's like, no.
And
Uh-oh.
I will have this one for you guys tomorrow because we'll probably work off of this one tomorrow and then switch back to this packet after that. Don't lose this one. I hole punched it and stapled it for you. We'll probably have. I mean, there's got to be 200 problems on here. Don't worry. You're not going to do 200 problems. That's just crazy. But it's just a multitude of extra styles of these things because the more practice that we can try and do, because really over the course of the next few days, we're going to be doing problems together a lot, and then I'm going to show you guys where this gets into play and why we need to use them in order then for us to be able to do the trig identities with equations. And we have that.
When are you doing that?
That'll be next week.
What part of next week?
I don't know. Someday. All right, so this first one is the trig identities puzzle. Try and get through those. You probably want to use a separate sheet of paper. You're going to move the spaces. You're not going to get room to do that. And then we'll check this stuff out tomorrow. So obviously, if your answer spells something that doesn't make any sense, you done goofed.
Wait, how much is this?
For tomorrow, I'll try to get through the first page.
Wait, like the puzzle and everything, or just like
Yeah.
through 12?
That would solve the puzzle, yes.
What if I just solved the puzzle?
Wait, but then what's this?
Those are the answer keys for the puzzle.
I got it now.
Translate this for me.
Hello, my name is Emma. It's a beautiful day here in the kitchen. Thank you for the introduction. Hello, everybody. Hello, everybody. I'd like to talk about the cuisine creme brulee. This is the recipe. For the recipe, you need 6 eggs, 40 centiliters of liquid cream, 25 centiliters of bait, 20 grams of
It's milk.
milk. Oh yeah, latte. There you go. 200 grams of sugar.
Yes.
In France, hi. What's up? How are you? I'm speaking French today.
I was wondering. Hey, I was wondering what you were doing. So.
She asked me to translate it, so I'm just randomly saying
You're
words.
speaking the French.
I am. Bonjour. Oh, français.
Well, we're at a meeting and we got.
Hey, we're doing trig identities. Want to do trig identities?
Hey, I've been seeing you since we were. It's been a long time.
You want to do trig identities?
Of course they do.
Come on, look at these things. These
Your
are
hair looks
fun.
so long.
Wrong button. They're fun. Look at all that.
I'm a fan.
How are you?
I'm good. How are you?
I haven't done this since I was like this. So.
Yeah.
And now that I'm 100, I just.
I'm older than you, so don't worry about it.
Not by a lot.
It's older.
Not by a lot.
So it makes you 101.
101.
So look at it that way.
Okay, well, now that you're doing scary math.
It's not scary. It's easy stuff.
She likes Y equals MX plus B.
That's right. That's my jam. That's my
Nope,
jam.
this is my jam.
That's you can do.
Show us. What did
What,
what did you just do?
What? You don't do that?
I don't use smart.
No. Oh, I didn't show you the thing. Wait.
By the
Just
way,
give me a paper
it
cup.
said, "Hello, my name's Emma, and welcome to my cooking show." It didn't say it's a beautiful day.
It's close enough.
You cannot write that in the end.
I'm looking at you going like, who is this child? I didn't recognize
Are
you
you
with the
serious?
blonde and being grown up.
Wait,
I'm like,
really?
that voice. I know.
Hit the light. Hit the light. This is for you.
I legit.
Oh,
I
knew it right away.
But I got golf clubs. Oh,
Did you really?
yeah.
Mr. Simpson Shush. Disparaging the boot is a bootable offense. It's one of their proudest traditions.
My volleyball shirt.
Is that a butt?
Oh, what is this? What is this?
Simpsons, the boot.
Oh, I see.
Oh, I can show you that tomorrow.
Or I'll boot your prime minister. I'll do it. So help me God, I'll boot him.
Sorry, I thought it was funny.
He's just like over here cracking up and just
Kathleen, don't hate me.
What time does the bell ring?
In like a minute.
Ooh, we should. No, wait. Well, I don't want to be in the mix when the kids are. The hallway's a scary place in between classes. Is that true?
Yeah.
Mr. Braga, is that true?
I think it's scarier in middle school.
It's a workaround.
Am I? Do you carry baby hands in
Okay,
your
this thing
like
said
your
hallway was
brother?
messed up.
He oftentimes will just randomly.
I want.
I love it. Yeah, when I'm walking by and I just see like a baby hand on the table and I'm like, what in the world?
See you guys. Have a good
And
one.
it was Naldo's brother,
Okay.
who's very funny but doesn't say words very often. But when he does, they're funny words.
That's awesome. Are you leaving tomorrow?
Yeah.
Good luck.